Welcome back. We're going to now be looking at counting the number of elements inside of sets. So first off, notation. When we're counting or finding the number of elements inside of a set, the notation for that is n in brackets and then whatever the name of our set is. So when we read n of A, that's the number of things inside of A. And if you have a small set, then it's a really easy question. So here I've got two sets, A and B, and if you wanted to know the number of things in A, I would count them, 1, 2, 3, 4, 5, 6, 7. So the number of things in A is 7, and for B, there's 5 things. Number of things inside of B is 5. For the obvious part, this course is called Finite Mathematics, so we are not going to care too much about things that are infinite. Although there are sets that are infinitely large, we are not going to bother counting them for obvious reasons. We are not interested in infinite things. A couple of things further, the empty set, you can say that since it's got 0 things in it, you could say the number of things in the empty set is 0. So notice again, I've said this a couple of times, but good to say one more, the difference between 0, which is a number, and empty set, which is a set containing no things. So the empty set is not 0, but the empty set has 0 things inside of it. Now, if your universe is small and you need to know how many things are in A intersect C, then you could just list everything and then just count everything yourself. For bigger sets, on the other hand, you may not want to list everything. So we may need to have some counting techniques and some formulas to help us out. Let's do an example. And we're going to start with a nice one where we've got a small universe. So this universe only has 7 things in it, so relatively small, which means if we're looking for anything like the number of things in A union B or anybody else, I can start off by first finding A union B and then just manually counting. So first off, what is A union B? So A has an A, B, and a C in it, and B has a B, C, D, and an E. I've already got the B and the C listed, so D and E. So if you now asked me how many things are inside of A union B, I just need to count, and I would say it adds up to 5 things. So the number of things in A union B is 5. A union C complement, how many things are in that? So first, again, a couple of steps. I'd find A union C, then I'd find A union C complement, and then I'd be able to count how many things are inside of A union C complement. So first off, A union C, anybody in A or C or both, A has an A, B, and a C in it, and C has an E, F, and a G in it. So that's almost the entire universe. The only person who's not there is letter D. So D would be the one thing inside of A union C complement. And that means the number of things inside of A union C complement is 1. And let's do one last. This one's going to take a few more steps because, again, we've got a few more things to figure out. Before I can count, I'll need to know what is A intersect B. I'll need to know what is B intersect C. I'll need to know what happens when we take A intersect B and B intersect C and connect them with a union. And then once I've done all of that, then I can count. Then I'll be able to say how many things we have in A intersect B union with B intersect C. So let's start with A intersect B. Where does A and B, where do they overlap? A has A, B, C in it. B has B, C, D, E in it. So there's a B and a C in common. B intersects C. So looking at B, B, C, D, E, C, E, F, G. What do they have in common? They just have a single element, which is E. And now if I said A intersect B union with B intersect C, I would say, well, that would be anybody in the first set or in the second or in both. There's no overlap, but there's the B and the C from the first one and the E from the second one, which means there's a grand total of 3 things inside that set. So number of things in A intersect B union B intersect C, that would be 3. Okay, this is a very important counting principle, the inclusion-exclusion principle, and there's sort of 2 variations on it. There's the first one, which is the more general one, and I'll talk about that for just a moment. We've got 2 sets, A and B, and we want to know how many things there are in A union B. So I'm just going to draw a Venn diagram for a moment, because that'll kind of explain where this formula is coming from. So we would like to know how many things are inside of A intersect B, which are inside of these 3 regions. So we want to know how many things are in all of those 3 areas all added together. So what happens if I were to just add up everybody inside of A and everybody inside of B? So if I took all the things inside of A, I would get just the A things plus the overlap. And if I added in all the things that were inside of B, then I would be getting all the individual just B things, but I would also be getting the overlap again. So that means that middle, A intersect B, it's being counted twice, and I don't want it to be counted twice. That's the reason why we have the subtraction there, that if I take all the things in A and all the things in B, that means we've counted everything, but we've counted the middle 1 time too many. So to balance that out, we subtract the intersection. We subtract A intersect B. Now, good news, if you happen to have disjoint sets, if A and B don't overlap, then the number of things in A intersect B would be 0. So in other words, the number of things in A union B would just be the number of things in A plus the number of things in B minus nothing. So we have a much more compact formula. So that's something else to notice for the future, that when we're talking about the inclusion-exclusion principle, I'm talking about unions, and that's where inclusion-exclusion is used for. And sort of generally, that inclusion-exclusion is telling us that unions are basically addition, that we have to be a little bit careful if there's an overlap, but if the sets don't overlap, then union essentially means just to add things together. So let's take a look at an example. And for this one, we need to be a little bit cautious with the reading. So first, when I'm reading this question, I have to make sure that I'm not adding extra words to it. So when I read this story, I've got a crafting club, there's 50 members, and it says 30 of the members knit. You'll notice I didn't use the word only there. I didn't say that those members only knit. So those 30 people who knit, they potentially also are doing other things. Maybe they're crocheting, maybe they're doing needlepoint, but they're knitting, maybe doing other things. And same thing with the 27 who crochet. The 27 who crochet, some of them are going to be doing other crafts as well. So again, don't assume that there's the word only there. If I don't say the word only, then there isn't the word only. Because otherwise, you're assuming that you have only knitting people are 30 and only crocheting people are 27, and that's not exactly at all what it says. So what are we interested in? How many members do at least one of the 2 activities? So first off, I'm going to define 2 sets. I'm going to say let A be the set of people who knit, and I'm going to have B being the set of people who crochet. And so if I wanted to summarize the information we've been given, I've got a few things that I'm just going to write on the side. First off, the universe is the 50 members. Those are the people we're talking about. And there's 30 of those 50 people knit. So inside of set A, there's 30 people. And inside of set B, there's 27 people. And finally, inside of sets A intersect B, there's 18 people. And I know that because the 18 people are knitting and crocheting. They're doing both activities. So those 18 people are inside of set A, and they're also inside of set B. So there's 18 in the overlap. So what that means for us is, yes, there are 30 people who knit, but of those 30 people, 18 are people who also crochet. And yes, there's 27 people who crochet, but of those 27 people, 18 of them also knit. So if I'm interested in the number of people who knit or crochet or do both activities, in other words, doing at least one of the two activities, A union B, using my inclusion-exclusion formula, I'd take the number of things that are in A plus the number of things that are in B minus the number of things that are inside of both, the number of things in A intersect B. So I have 30 people who knit and I have 27 people who crochet. I've counted the people who do both activities twice now, so to account for that, I need to balance that out with subtracting. So 30 plus 27 minus 18, that should be the number of people who are, those are the number of people who are doing at least one of the two activities. So that means knitting or crocheting or doing both. So 39 people in total. If we're thinking about the doing neither of the two activities, so you are not crocheting and you are not knitting, I'm going to just sort of draw a Venn diagram here because this is something where I don't necessarily have a formula, but if I'm thinking about a Venn diagram, that'll sort of help me out. I know that regions 1, 2, and 3 all add up to 39 because that's what we just found, that there's 39 people in these three regions. But I also know that there's 50 people in the universe in total. So that means that the difference between the 50 people that I have in the universe and the 39 people who are inside of A union B, that should be the people who are outside of A union B. So if I'm looking for people who do neither of the two activities, so if I'm looking for the number of people who do not knit and also do not crochet, I could say, well, that's just the 50 people that we have in the knitting club, and I'll take away the 39 people who knit or crochet or do both, and then I'll be left with the people who don't knit and also don't crochet. This technique that we've used here, we're going to see this in future, and this is called counting the complement, using the opposite to find something. So here, to find the number of things that are in the exterior inside of region 4, I used the fact that I knew what was the opposite. I know what was going on in regions 1, 2, and 3. Since there's 39 people inside the two sets, then that means there are 11 people outside. De Morgan's laws we mentioned at the very beginning of this section. So just as a reminder, we had shaded A complement intersect B complement and found that it looked the same as A union B all complemented. So those two expressions mean the same thing. You can change one for the other. And same thing for A intersect B all complemented. That's the same thing as A complement union B complement. This isn't the most important part of the course, but I think it's a nice thing just to think about using sets abstractly. So let's, without further ado, do an example. I've got a couple of expressions and I just want to use De Morgan's laws to simplify these things. So I'm just going to apply De Morgan's law from the previous page and say, well, I know, according to De Morgan's law, that A union B whole thing complemented should be A complement intersect B complement. So that first little part, I've now turned it into A complement intersect B complement. And I could simplify a little bit further, because if you're reading what we have here, outside of A and outside of B and outside of B, I've just basically repeated myself. That extra and also outside of B, that's not necessary. I could really say, well, that is the same thing as being outside of A and also outside of B. And that would be a nice, more compact way to express that. For part C, or part B rather, I have C complement intersect D complement whole thing complemented. So looking at that, I'd say using De Morgan's law, That would be a C complement complemented union a D complement complemented. We've kind of said this before. We saw this earlier on when we found B complement complement, and we said, oh, well, that's the same thing as B. So same sort of an idea here. C complement complement, the opposite of C should just be C. And for D complement complement, the opposite of D should just be D. So that original expression, C complement intersect D complement, whole thing complemented, really just boils down to C union D.